Hello and welcome to Gaffley's Grinds. In today's video, we are going to do a quick walkthrough of some questions about the third titration on the Volumetric chemistry course. Now, this titration is very similar to the first one, where we are going to react a strong acid, so hydrochloric acid, with a weak base sodium carbonate. But this sodium carbonate is not pure powdered form as it was in the first one. Instead, it's in the form of what we call washing soda crystals. Now, you don't really hear much about washing soda nowadays, but years ago in your parents' or your grandparents' time, this would have been something they may have used to wash clothes in or as like some kind of a detergent for cleaning windows and that kind of thing. So there were little white crystals and they were called washing soda. Now, how is washing soda different from sodium carbonate? We're going to have a look at this now. As you can see, washing soda here is also called hydrated sodium carbonate. And the aim of this titration is to determine the amount of water of crystallization in these washing soda crystals. So what I'm going to do is I'm going to get you to pause the video and read some of the theory. So this paragraph here, that paragraph down to about here, I'm going to get you to pause the video and have a quick read of that yourself. Right, so it's pretty self-explanatory, I suppose. You should only be playing if you have gone ahead and watched this. But basically, yeah, as you read there, some substances, as they form crystals, they absorb water molecules when they do this. So here's an example, copper sulfate, CuSO4. And when it's forming crystals, for every one molecule of CuSO4, 7 molecules of water are absorbed and attached to the crystals. Well, washing soda is similar, or sorry, sodium carbonate is similar. When it forms solid crystals, it absorbs some water molecules. Our job is to find out how many water molecules per molecule, basically, is what we're trying to do here. So, yeah, we have been given Na2, so sodium carbonate, XH2O. Now, X is equal to a number, but we don't know what that is. That's what we're trying to determine. X equals question mark. How many water molecules are attached to the sodium carbonate here? Now, generally in this titration, you'll be asked to calculate for two things. First of all, the percentage of water crystallization. So out of the crystals you weigh out at the start, how much of it is sodium carbonate and how much of that mass is water. So obviously, if there's 2 grams of crystals, maybe 1 point something grams will be sodium carbonate and the rest of the grams will be the water of crystallization. And then from there to work out the value of X. Okay. So some points to make. A little bit of background about the titrations. Sorry about that. So quick background to the titration. This is a strong acid, weak base titration. So you remember the acronym SOB-MO. So strong acid, weak base, MO. Methyl orange, therefore, is the indicator. So as you can see here, the indicator for this titration is methyl orange. Methyl orange is yellow in a base, and it turns to a red or pink in an acid. So there's your color change. When it's in a conical flask with the base, with the sodium carbonate, it's yellowy. And when it reaches the end point and the solution turns acidic with red. Here's your balanced equation. And obviously then your ratio of your 2 reactants, 2 hydrochloric acids for every 1 sodium carbonate. So at this point, I think you guys should be able to do a few of these questions. So as you can see here, the questions are numbered 1, 5, 3. Well, definitely 153 and 154, you guys should be able to do at this stage. So let's pause the video and have a go at them now. All right, so we're always coming back to remind ourselves of what a standard solution is. Remember, a standard solution is the one whose concentration you know. So in this particular calculation, our standard solution, well, we don't know anything about this one. We know we're going to try and find the percentage of water crystallization and the value of X. So hopefully it's pretty obvious that the concentration of this, we don't know the concentration of sodium carbonate or of water. So this is our unknown concentration, and that must mean that our acid is a known molarity, and they'll have to give you that in the question. So which is your standard solution? It's the HCl. Well done if you said that. And how do you know? Well, it's always the one whose concentration is known. That's what standard solution means. It means you know the concentration. All right, so now we're moving on to discuss the actual calculation parts of this question. So as you can see here, it says in 155 below is an example of an exam question. Identify the important information in the question. So I'm going to go to 155 and I'm going to get you guys to look at this question down here, and I'm going to ask you to pick out the important information. Like I said, I always get students to rewrite this out And then I'm going to ask you to find the volume and the concentration for the what do you call it, the acid and the base here, the two reactants. Okay, now obviously one of these is going to be an unknown concentration, and the other one you've got a little bit of work to do. You're going to have to actually, does it give you the concentration of, oh, it does give you the concentration of one of them, and it doesn't give you the concentration of the other. Okay, so rewrite this out, write down the volume used of each in liters and the concentration of one, and then the other one is an unknown concentration. So pause the video and try doing that now, please. All right, this is what you should have done, and you should only be watching if you have had a go at that, because again, you don't learn anything from copying from me. You have to have a go. So this was the equation. It was Na2CO3 plus HCl. So there's our acid and our base, and they react to give 2 NaCl plus CO2 plus H2O. And like I always say, the products are really not important in a titration. We're interested in the reactants. All right, if you haven't done this already, I always ask students to label which one's the acid and which one's the base, because this is an acid-base titration. Do that now if you haven't done it already. What you should have said is that the HCl is the acid and the Na2CO3 is the base. Okay, so we got our acid and our base. And then, like I always say, take arrows out here, like this, one set of 2 arrows for the acid and one for the base. And what I want is, I want the volume of acid used in liters, the volume of the base used in liters, and remember this is the volume used in each of the titrations, the average volume. And then one of these will be a question mark molarity, and one of these will be a, apologies, yeah, and one of these will be a known molarity. So again, pause the video and fill in these blanks if you haven't already done this. Right, so I'm going to my piece of text and I'm reading here and I'm seeing what's important. It said an experiment was carried out to determine the percentage of water crystallization and the degree of water crystallization X in a sample of hydrated sodium carbonate crystals. Okay, now I've just become aware that I did not have this screen up when I asked you guys to do that. So now that I have the screen up, if you need to pause and try and figure out what's on those arrows, you can do it now. All right, it says an 8.2 gram. So this was how much was actually weighed. This was how much was weighed of the sample of crystals, was accurately weighed on a clock glass and made up to 500 centimeters cubed of solution in a volumetric flask. So this is our original solution of Na2CO3. Now, of course, we didn't use all of that in each titration, I don't think. So let's go ahead and see here what it says. It says a pipette was used to transfer 25 cm cube portions of this solution to a conical flask. So now we're getting to the information that's important about the base. We use 25 centimeter cube portions in a conical flask. So over here, that is this guy here that we've been talking about. Okay, and we use 25 cm cube portions. Now I have a volume in liters. So I've shown you in the first two videos how to convert from centimeters cubed to liters. So pause the video, go ahead and write that volume down now. Okay, what you should have said here is you should have said 0.025 liters. This should be getting really automatic and really easy for you going between centimeters cubed and liters. Back to the text, what does it say? A previously standardized 0.11 molar solution of hydrochloric acid. So there's information, look, we have a 0.11 molar solution and that's of the hydrochloric acid. Let's go back over here and fill that in. This is 0.11 molar. Was used to titrate each sample. A number of accurate titrations were carried out, and the average volume of the HCl. So here's where we're going to find our numbers of liters of HCl per titration. Sorry. Sorry, my OneNote's a bit glitchy here. Yeah, here we go. Here's the hydrochloric acid, and here's the volume, 26.05 cm cubed. Now remember, that we need that to be in liters. So pause the video and go ahead and write that down in liters. Okay, I'm going to check the number again. It was 2605, so that should be 0.02605. Okay, 0.02605. Now, if you got that right, well done. And again, my suggestion is always to do this in liters here at this stage. That means that this here is going to be our unknown. Let's go check that anyway, just in case. Let's go check the questions down below where it says, It says here, find the concentration of the sodium carbonate in moles per liter. There's the first question, which is exactly this here. So that's what we're going to be trying to find. Okay, now let's read what it says and plan out our question. Okay, at this stage, what I'm going to say is, okay, let's just go up here and see what it says. It says we have question 155 done. It says 156, answer part D. This is straightforward. It's the same as all the other titrations that you've done so far. So part D is asking us to find the concentration of sodium carbonate in moles per liter and then in grams per liter. If you guys know how to do that, then you guys are ahead of the curve. You can pause the video and try to do that yourself. Again, it's always a good idea if you're anyway confident with this that you have a go yourself and you only play for help, okay, that you really are trying to push yourself on and do this. So pause the video and do that now if you can. All right, if you can't do it, I can help you plan this out. And this is a really good practice to get into. Let's figure out what we've got to do. Let's start with what we know, this here. We know both of these, okay? So what we can do here is we can go from moles of HCl per liter, moles per liter, which is obviously this here, molar, and we can go from moles per liter and find out, well, how many liters or how many moles would we have in the quantity we used, moles of HCl. Okay, so this is the amount we used, and we know there's this many moles per liter. So we can go from moles of HCl to moles per liter of HCl to moles of HCl used. From there, then, we can then convert and find out, well, if we use that many moles of HCl, how many moles of Na2CO3 reacted with that? Most of you should know how to do that. Again, if you don't know how to do that, we can get you some help as we go along. Then we've got to find the answer in moles of Na2, but moles of Na2 per liter. And then we've got to convert. And by the way, that's part one done. That's D part one, the answer. And then for D part two, it asks us to give our answer in grams of Na2CO3 per liter. So now that I've helped you plan this out, the steps that you've got to do. So this would be D part one. When we get to here, molarity. And then D part two is to convert that to grams per liter. All right, definitely most of us should be able to pause the video and have a go at this now, okay? All right, so at this stage, this is for watching along, checking your answer, or if you really need more help, then you can be watching along. All right, so let's begin with what we know. How much HCl do we have in moles per liter? Well, we know from laying out our question that we have 0.11 moles of HCl in every liter. We know that. It's up here. Molar means moles per liter. And we want to get how many moles of HCl that is. Okay, so that's, we want to go how many moles of HCl was used. Mole of HCl. And the way we do that is get this one liter to cancel out. And we can do that by timesing it by a volume in liters. And the volume in liters was this amount that we used. So if we times it by 0.0205, then we'll get the number of moles that was used. So hopefully that's what you did. Well done. If it is, go ahead, pause the video and do this calculation now. Okay, so what you should have done is you should have got that this would be 2.8655 by 10 to the power of minus 3 moles of HCl. So if we had that many liters used, that's how many moles we would have used. All right, so that is this bit done. And not watch how I tick off the plan and I keep track of everything. Then I want to find out how many moles of Na2CO3 would this react with. Okay, so what we need to do here is we need to look at the balanced equation. Now I've taken something down wrong here. This is a great chance for me to highlight what you should not do. I am missing something from the balanced equation. If I go back over here, you should see that I'm missing this 2. And this 2 is going to mess up your whole question if you don't include it. So I'm going back here and I'm putting my 2 in. And I'm lucky I spotted that. Otherwise, I'd be losing some marks there. So the next thing to do is think about your ratio. There's 1 molecule or 1 mole of Na2CO3 for every 2 moles of acid. So back down here, how do we convert from moles of HCl to moles of Na2CO3? Well, what I want to do is cancel out moles of HCl. So set up your conversion factor and you do moles of HCl to moles of Na2CO3. From your balanced equation, what are those numbers? Pause your video and write them down. Okay, what you should have done is one of these for every two of these. So you pause your video now and do this calculation to find out how many moles of Na2CO3 will be left. Okay, 2.8655 by 10 to the minus 3. And then, of course, it's essentially timesing it by a half. So the answer that I'm getting here is 1.43275 times 10 to the minus 3. And that, of course, this is this unit that's left over, moles of Na2CO3. So that has got me up to here. All right, so the last thing I need to do to finish D part 1 is to find out how many moles per liter that would be. Okay, now, of course, this was the amount of moles per titration, but the amount in a titration was not 1 full liter. So I need it to be in moles per liter here. So you see what I've done? I've added a denominator that has liters. So I have moles per liter, and that's what I wanted in my answer. Good. Now I need to know what is the number of liters I used in that titration. So again, you have the opportunity to write down that volume now. Pause your video and do that now. Okay, of course, this was the volume that was used, 0.025. Okay, so that's the number I'm going to put down here, 0.025. And you pause the video and you should get your first answer to D part 1. And this is going to be probably what, 6 marks of the question here. All right, so when I do that, I get answer divided by 0.025. I'm going to get 0.057 is what I'm getting. 0.05731 is actually what I got. And of course, that's molar Na2CO3. All right, so at this stage, what I think is always a good idea as well is to highlight that this is D, sorry, in red maybe, different color, make it stand out, that this is your answer to D part 1. Come on, red. D part 1. All right, brilliant. Now for D part 2, we have to go to grams per liter of Na2CO3. Of course, we know that molar, or hopefully everyone knows that molar is the same as saying moles over 1 liter, moles per 1 liter. Okay, so all I did was change that. It's still molar. And I want to go to grams per liter. Okay. So again, at this stage, most of you will know how to do that, convert from moles per liter to grams per liter. I always get mine to do a conversion factor like this. And then equals, we know in our answer, we want to be a certain amount of grams of Na2CO3 per liter. So what needs to be on this fraction here to turn it into grams per liter? So pause the video and figure that out now. Well, of course, I need moles per liter to cancel because it's not anywhere in my answer. So I need moles of Na2CO3. I need that to cancel. So cancel that. And what I need to convert to is grams of Na2CO3. I can leave the liter the way it is because look at what I need in my answer. I've got liters here and I've got liters here. And now I've cancelled the moles and I've been left with grams of Na2CO3. That's what's over here. So good. So this is grams over, gram per. All right. So that's how conversion factors work. My students should be very familiar with that. So the next thing is for 1 mole of Na2CO3, how many grams is that? So pause the video and work that out now. Okay, when you work that out, it's the molar mass, of course. It's 106 grams of Na2CO3 for every 1 mole. Pause the video and figure out how many grams this is then per liter. Okay, so when you do this, you should get actually, I'm just going to make a little bit more space, 6.07486 grams in 1 liter. And that is your answer to D part 2. So pretty standard up to there, okay? And hopefully most of you were able to do that bit by yourself. All right, so that's 156 done. You'll see the next bit says answer part E. Remembering that the original solution was 0.5 liters. No, sorry, I'm going to go away from that and we're going to analyze this actually by itself here. Okay, so the next thing we need to think about is part E. Let's see what part E says. Part E says calculate the percentage of water of crystallization present in the crystals and therefore the value of X. Okay, so let's break down into two parts, E part 1 and E part 2. Find the percentage of water of crystallization. What percent of the crystals, the original crystals, was water? Okay, so let's plan this out. What are we going to do? We're going to use this number again, by the way, because we know that we should have 6.07486 grams of sodium carbonate in every 1 liter. That's the concentration. So what we're going to do is we're going to find how much of it is water then. All right. So remember, we have a volume, we have a concentration in grams per liter of sodium carbonate, Na2CO3. And what we want to do is go to how many grams of sodium carbonate was in our original solution, grams of Na2CO3. Because remember, the original solution was not 1 full liter. How much was it? We'll go back to the text for this. Let's see. It says 8.2 grams of crystals were weighed out and the solution was made up to 500 cm cubed. So that's not a full liter. So remembering that 500 cm cubed is how many liters? So most of us should be able to try and do that in our head. It's 0.5 liters. Okay, so that's our first step, is to find out how many grams of sodium carbonate should have been in the half a liter. Once you have that then, and I'm going to let you guys try and work your way through that, then we're going to find out, okay, we know what the mass of crystals was. Mass of crystals. We know how much we weighed out, and we can get that information in the question, and we want to take away what was our mass of sodium carbonate, Na2CO3, which is from up here, how much mass of sodium carbonate in the half liter. And of course, if you take the mass of the crystals and you take away how much of it's sodium carbonate, and that should give us the mass of the water, because of course the rest of the crystals are water. So some of it is this, the rest is water. The percentage water then can be got by doing the mass of the water over the total mass of the crystals. And timesing that by 100 to turn it into a percentage. Okay, so at this stage, you guys should be able to work your way through that. My advice to you is maybe to write down this plan. Okay, and now that you've done that, I'm going to put back up the text so you can see the information that was given in the question. All right, and I'm going to get you to pause the video and work your way through until you find the percentage of water in the crystals. All right, I'm going to show you how I will do that now, following this plan. So I have the plan in red, and I'm going to do the sum beside it in black here. Okay, so we know we had that should be black now. We had 6.07486 grams, 86 grams of Na2CO3 per every 1 liter, so per 1 liter. And we didn't have 1 liter, we had 0.5 liters. So in 0.5 liters, it should be half of that amount. So when you did this, and you cancel out the liters and left you with grams of Na2CO3, you should have got 3.03743 grams of Na2CO3. Well done if you got that right. So that means that when you weighed out the crystals, this much was sodium carbonate. Okay, of course, we then need to do crystals minus Na2CO3 equals water, the mass of the water. All right, from the text, what you should have remembered or learned is that the crystals were weighed out was 8.2 grams. Let's go check that. I always like to double check my numbers, and you should do the same. Yeah, look, here I have it highlighted as being weighed out, 8.2 grams. So 8.2 grams was weighed out. And we know that we're going to take away the amount of that was the sodium carbonate. So 3.03743 grams was the sodium carbonate. So when we take that away, we should get the rest, the remainder. Well, it had to be water because that's all that's in it. It's water and sodium carbonate. So 8.2 take away 3.03743, getting a number 5.16257 grams is water then. So how much? So that's quite a lot of it. And eyeballing this, you should be able to see how much of it is water. Well, it's got to be more than half. Look, this is bigger than this. So it's more than half is water. So I'm expecting a number greater than 50% here. If I don't get more than 50%, then I must have done something wrong. And I know myself that 5 is more than half of 8. So I'm just using rough numbers there. All right, so to get my mass and my percentage water then, percentage water, I'm going to do my mass of water, 0.16257. Okay, and if you didn't get this right and you're on the right track now, pause the video and finish off this calculation to get percentage water. Okay, so that is that, and then we're going to divide by the mass of the crystals, which is 8.2, and then times by 100 to turn it into a percent equals. And what you should have got is 62.96% of the crystals were water. 62.96%. All right, well done if you got that by yourself. If you got it with a little bit of help, good stuff. If you needed a lot of help, again, my suggestion is to take what you've learned here and find another question on this titration about water crystallization. Keep practicing them until it becomes easy. Right, the last part of the question then, it's stuck in here. It says to find the value of X, which is the degree of hydration in the crystals. Remember, so far we have Na2CO3.X H2O, and we want to know, well, what's the X? How many molecules is that? Now remember, we can think about this in moles. If we have 1 mole of this, then we want to know how many moles of this. Okay, so 1 mole is to how many moles? So we can think of it like a ratio. And that's what we're going to do here to help us figure this out. So how do we do this? So to find X, what do we want to do? Well, we want to do moles of H2O to moles of Na2CO3. That's what we want to find, the ratio of moles of water to moles of Na2CO3. So using your masses and the molar masses of these substances, can we find how many moles of each of these we have? Some of you will be able to pause the video and be confident to go and have a go at this now. Okay, if you weren't confident, let's think about how we would do this. How do we get the moles of water? Well, of course, we have the mass of water that we have in the crystals. We work this out, divided by the molar mass of water. Molar mass of water. So the mass of the water we had in the crystals over the molar mass of H2O. Okay, and then of course, to get the moles of the Na2CO3, it's the same thing. The mass of Na2CO3 in the crystals that we've worked out earlier over the molar mass of Na2CO3. All right, let's do that step now. Okay, so most of us should be able to do that. Okay, what we're going to do here is the mass of water first. So the mass of water, remember, was this guy here. That was the mass of water. So we're going to do 5.16257 over the molar mass of water. So this is grams over the molar mass of water, which is 18. So H2O, remember, H2O is 16 for the oxygen and 2 times 1 for the 2 hydrogens. So equals 18. That's where that came from. If you're not sure how to find molar mass, we're in trouble. Hopefully, that's really simple and straightforward here. And then we're going to do the same for the mass of the sodium carbonate. So I'm going to get you to pause the video and finish that off if you haven't done it already. All right, so here is the mass of sodium carbonate in the crystals. It was 3.03743. And we're dividing that by the molar mass of sodium carbonate. Now, don't be silly and work it out again because we did it earlier over here. Remember, here is the molar mass of sodium carbonate, 106. So use it again. Don't do the same work twice. And let's find out how many moles of each of those we have. Go ahead and do that calculation now. Okay, so the numbers we should be getting when we do these calculations out is that this should be 0.2868 is to this many moles of the sodium carbonate, 0.0286. Now, what you should be seeing is that this here, if I eyeball this here looks to be exactly 10 times that there. That's what it looks like to me. But to find out for sure, what we should do is take both of these and divide by the smaller one. So this here is the smaller one. Okay, this is obviously the smaller number. So what we're going to do is we're going to take both of these, 0.0286, and we're going to divide this by 0.0286. Okay, so divide both by the smaller is what I'm doing here. Divide both by smaller and find out how many times bigger is the bigger one, in other words. Of course, this will go into itself once, so we should always have something to 1, and then when you do this on the calculator, you should pretty much get a number which is around 10. Now I'm going to do it here and find out exactly what I get. 0.2868 divided by or over 0.0286. And the number I'm getting is 10.02 or 10.03. And always when you're doing ratios like this, you should round to the nearest number. So 10 to 1, okay? So what that means here is that the formula here is Na2CO3.10H2O. And it should always work out, you should be very close to a whole number, 10 to 1. So that there is the final answer. Even if you only had this line here, you'd probably get all the marks for this. Okay, but this just tells us that this is the correct formula. So a tough little question, especially this last bit in red. If you want to make notes here of how to find, this would be notes on how to find X, which is the amount of water of crystallization. This is definitely the hardest of the acid-base titrations, but again, they're all quite similar when they come up, okay? It's the same steps that you got to follow. So again, my advice to you now is to find another similar question in your exam papers, which asks you to calculate X, the value of water of crystallization, and practice it. And if you've got, find another one and another one, and you've got to just nail these out of the park until they're automatic to you, okay? There's not only one way to do this. Your teacher may have showed you other ways to do this. There's lots of ways to do this. You can use ratios. You can use a formula. And if you're wondering why I'm not talking about any formulas like grams or, you know, that number of moles equals grams over molar mass, stuff like that. I just find that if you're only using formulas, you run into a lot of problems when a question is different. And students don't really understand what they're plugging into the formula. They don't really understand what's actually going on. And what that means is that you just get lost and you get confused. Now, you may get lost and you may get confused in this way as well. But this way encourages you to really think through the problem and follow a logical sequence. So stuff like this, how I planned out what I should do, this line here. Like, you can only really do this if you understand. This is what we call, by the way, all the stuff that I'm doing here is what we call a first principles method. And you've probably heard of that in maths, first principles method, where you actually can see all the maths. It's not hidden in a formula. And you're thinking your way through the problem one step at a time, planning it out. There is a formula you can use for titrations, but they only work for a little bit of it. And then you have an answer that you don't really know what to do with. And like, this is a much better, easier way of planning your way through it. If you have any requests or you'd like any specific question in your exam papers done on titrations, stick it in the comments down below this video and I'll see it and I'll get around to it as quick as I can. All right, guys, thank you. Hope you found this video helpful. If you can like the video, help other chemistry students find the video, that would be great. And I'll see you in the next one.